Okay, so generalising that then, rather than just taking roots of the number 1, we can take roots of any number. And it turns out that for any number in the complex plane, except for 0, there are exactly nth roots. These roots will always be vertices of a regular n-gon. So if n was 4, it would be a square, 5 would be a regular pentagon, 6 regular hexagon, so on. Centred on the number 0. And these complex numbers will have the same modulus, and their arguments will be the same distance apart from one another. And we use this concept to our advantage to find the roots of complex numbers. So just to illustrate the one that I did previously, I cube rooted number 1, and I got these 3, and they form an equilateral triangle centred on the number 0. If you take the fourth root to the number 1, you get 1 minus 1i and minus I. We can clearly see that's a square centred on the number 0. And the fifth roots, you get a nice little pentagon there. And the argument here is half of the argument here, and similarly the argument of this one is half the argument of that one. Okay. So we use it to our advantage. In general, we have the argument of z to the n as being theta, and we have the modulus of z to the n as being r. This implies that the modulus of z is equal to the nth root of r, as perhaps you might expect, and the argument of z is equal to theta divided by n, but you may add any k times 2 pi on n, such that k is an integer. And this will allow you to find all the other arguments that satisfy z to the n equals, well, whatever number you're given. So that's the theory. Let's have a look at a couple of examples. So find the 5 fifth roots of 4 plus 4i. Okay, there are 5 fifth roots of 4 plus 4i. So what we're going to do is we're first of all going to calculate the argument of 4 plus 4i. Without too much thinking, that is pi on 4. And the modulus of 4 plus 4i, well, that will be root 32. Okay, root 32 can of course be written as 4 root 2. So this then implies that the argument of any fifth root of 4 plus 4i must be equal to pi on 4 divided by 5, okay, so that's n, and then we can add any constant times 2 pi on 5, such that k is an integer, and that will give us another argument. In this case, we get pi on 20, and we keep adding multiples of 2 pi on 5. So we actually get pi on 20. Then if k is 1, we can add 2 pi on 5 to that. So 1 on 20 plus 2 on 5 gives us 9 pi on 20. Add another 2 pi on 5, gives us another one, which is 17 pi on 20. Add another one that's going to be 25 pi on 20, which can be simplified to 5 pi on 4, but that's bigger than pi, so as a principal argument that would be minus 3 pi on 4. And then the other one would be minus 7 pi on 20. So those are the 5 arguments, and I calculated the first one by just taking the argument of my original complex number and dividing it by n. In this case n was 5 to give me pi on 20, and then full circle we keep adding multiples of 2 pi on 5 to them, until we get back. If I add 2 pi on 5 to that, I'll get back to pi on 20. Add 2 pi on 5, add 2 pi on 5, and so on. So those are the 5 arguments that I get. The modulus of the fifth root of 4 plus 4i will be equal to the fifth root of 4 root 2. Fifth root of 4 root 2. So 4 root 2 was a modulus of 4 plus 4i, so therefore the modulus of the fifth root will be the fifth root of that. This is, of course, 2 squared, and that's root 2, so that's 2 to the half, so it's actually 2 to the 2.5 to the fifth. So it's actually just root 2. Okay, so the modulus is root 2. The fifth root of 4 root 2 is root 2. Just confirming that. Okay, so now we've got that, we can state our complex roots. So therefore, the 5 fifth roots of 4 plus 4i are, and you can state it in exponential form, so root 2 e to the pi I on 20, root 2 e to the 9 pi I on 20, root 2 e to the 17 pi I on 20, root 2 e to the minus 3 pi I on 4, and root 2 e to the minus 7 pi I on 20. Or you could write it in modulus argument form. So that's going to be root 2 into cos of pi on 20 plus I times sine of pi on 20. Or we could actually evaluate some of these. So I'm going to evaluate this one, because I know this was actually quite a nice number. So cos of minus 3 pi on 4 is minus root 2 on 2. So I get root 2 into minus root 2 on 2. And then sine of that comes out to be, again, minus root 2 on 2. I can bring the root 2 in there, and I end up with minus 1 minus I. So yeah, you could do it in Cartesian form. So exponential form, polar form, Cartesian form, it doesn't matter. Of course, if a question asks for a particular form, you must leave it in that form. Otherwise, you would lose marks. And finally, find the fourth roots of 12 minus 5i. So again, calculate the argument of this. In this case, we are looking in this quadrant, so 12 minus 5i is down here, so my argument will be a negative acute number. So I'm going to inverse tan minus 5 over 12. And that gives me minus 0.395. That's the 3 sig fig. And the modulus of 12 minus 5i is 13. That's what? Yes, it is. So therefore, the argument of the fourth root of 12 minus 5i is equal to that divided by 4. So minus 0.099. And then again, you can add multiples of 2 pi on 4, such that k is an element of the integers, to give you other arguments. So we've got minus 0.099, add pi on 2 to that. 1.472, 3.043, The next one's above 2 pi, so I'm going to, sorry, above pi, so I'm going to subtract 2 pi from that, and I get minus 1.669. If I add pi on 2 to that, I should end up back here, so I'm just going to check that, and I do. So those are my 4 arguments, and then the modulus of the 4th root of 12 minus 5i is equal to the 4th root of 13. So from there, again, I can set an exponential form. So 4th root of 13 e to the minus 0.099 I plus the 4th root, comma, 4th root of 13 e to the 1.472 I, the 4th root of 13 e to the 3.043 I, and the 4th root of 13 times e to the minus 1.669 I. And those are my 4 4th roots of 12 minus 5i.